Hey guys, welcome back to another video. Today we're going to be solving Leetcode 1648, cell diminishing valued colored balls. And this problem description tells us that we're given an inventory of different colored balls, and there is a customer that orders balls of any color. Okay, so we're told that for some reason the customer weirdly values the colored balls, and each colored ball's value is the number of balls of that color you currently have in your inventory. So we've got an inventory, and we have orders basically. So, for example, if you own 6 yellow balls, the customer will pay 6 for the first yellow ball. After the transaction, there are only 5 yellow balls left, so the next yellow ball is then valued at 5. So, if we had let's say this is a yellow ball, the value is currently 5. Once we pick 5, then it becomes 4, then it becomes 3. So this is every time we pick a yellow ball, the value of the yellow ball decreases. And we're given an integer array inventory, which represents the number of balls of the ith color that you initially own. Okay. And we're also given an integer array called orders, which represents the total number of balls that the customer wants. And we can sell the balls in any order. And we want to return the maximum total value that you can attain after selling orders colored balls. As the answer may be too large, return it mod 10 to the power of 9 plus 7. Okay, so this graphic here is kind of nice, but I mean it's quite simple just to write this down. So in this example, we've got 2 and 5. So of course, this is, if you haven't noticed, this is basically a greedy problem, right? We want to choose largest balls first. So in this example, we've got 5 and 2. Well, the orders is 4, so we can pick 4 balls, and we want to maximize the output, don't we? So we can choose 5, then we can choose, we can decrement 5 by 1. So actually, let me put it like this. So 5 and 2. So we've got 5, and this becomes 4 plus 4. This becomes 3, so plus 3, and then this becomes 2. Well, now we can just pick this 2, or we can pick this 2. Whichever 2 we pick is fine. And now we've got 5, 4, 3, 2, and the length is equal to order, so this is where we stop. And this is our output. This will give us the maximum value of all the balls that we can choose. So, let's look at another example. In this example, we've got 3 and 5, so we've got, 5, 3. So, we'll say 5 plus 4. So now we've got 3. Who do we choose? Well, we choose the first 3. This becomes 2. Then we choose the second 3. And then we choose the 2 2s. And then our output is equal, length is equal to 6. So then we just return this sum over here. Isn't that nice? So it's, going through examples makes a lot of sense, but you can probably see something that's it looks a bit too easy, does it not? And here we can tell why. We can see that the number is going to be quite large. If we keep picking, a number and then another number and then another number, we're not going to be able to solve this without getting a time limit exceeded error. It's not going to be an optimal algorithm to solve this like that, just by iterating one ball at a time, adding one ball at a time to our sum. That's not what we want to do. Instead, what we can do is choose entire chunks, right? So instead of, let's say we have these chunks over here, instead of choosing, 1, 2, 3, why don't we just choose the entire chunk? Why don't we just choose this entire chunk and this entire chunk? And then if we get to the point where we have orders, the chunk is bigger than the order, so we only choose a partial size of the chunk. And basically these chunks are obviously equal to the balls of a certain color. So that's the intuition behind solving this problem. It's going to be a greedy problem, and we want to have the same logic, the same intuition behind picking single balls, but we want to do entire layers. And I think it's important to notice, and I think we have this example over here. 3 and 5. So we can see when 5 becomes 4 becomes 3. Well, then we have 3 here as well. So we've got 2 3s. Then what do? Well, when we have 2 of the same, we want to go in layers, right? So let's say we have 3 and 3. We want to go to the first 3, the second 3, and the first 2 and the second 2. You can see there's a pattern here. We're doing these in parallel. So we can do that. We can factor that into our algorithm as well when we solve this problem. So when there are colors which have the same number of balls, then we will handle those concurrently. So yeah, let's actually get to coding this. So the first thing we want to do is I'm actually just going to paste in a helper function here, and you can look into the maths of this on your own. It's fairly simple, but basically it just returns a sum of the arithmetic sequence for each level, and we just need to pass in the high and low values, and it will give us the sum of the arithmetic series. So definitely I would recommend looking at the maths yourself, but this is one of those problems where you can't really derive the answer without knowing the formulas or how to solve this problem from a mathematical point of view. Unfortunately, I did try to solve this by using a heap, and although it is a valid way to solve the problem, it's not at the same time, because you do get a time limit exceeded error. So I had to kind of go with solving this using a bit of arithmetic. So the next thing we want to do is actually sort our inventory. Remember, we want to start with the biggest numbers first. So we want to say reverse equals true so that we get going in descending order. And now we've got our biggest numbers first. We can now add our sentinel. So we can say inventories.add, and we can just .append, and we can just add 0. And this is going to be our sentinel. It's going to be our terminator variable, basically. And then we can add a profit. Initially, this is going to be set to 0, and we can have a width. We can call this, we'll call this width. But basically, this width is going to be equal to the number of balls that have the same, or the number of colors that have, the number of ball colors that have the same count across different balls. So in this case, this would be equal to 3. This would be equal to 2. This would be equal to 1. So that's basically it. If we have multiple, we have multiple colored balls which have the same size, then we increment the width. So actually, this should be a 1 in that case. And then the next thing we want to do is say, let's actually go through the logic. So for each item in our inventory, length of inventory -1. Okay, so let's look at how we're going to solve this. Well, the first thing we can do is obviously increment our width by 1, but only if we know that the next ball stack is also shares the same value. So if it doesn't, if there is a level change, so this is a level change here, well then that goes, we can say if inventory I is less than inventory, or is greater than, is greater than inventory I plus 1. I think I should probably mention the reason we're doing -1 here is so that we don't go out of bounds. So in this case, there is a level change. So what we want to do is say if the width is actually, do we need to reset the width? Now that I think about it. No, I don't think we do need to. So the first thing we want to do is actually say if the width times by, I'll just copy this, inventory I minus inventory I plus 1. So basically the sum of all of these balls, the number of balls across the levels, times by the width. If this is less than orders, well then we have enough orders so that we can actually just add all of these levels, can't we? So we can say profit plus equals width multiplied by, and now we can use our very handy sum range function. So we can pass in sum range inventory I plus 1. Remember, we want to add the high value, actually low value first, and then high. So we can then add inventory I over here. So we're basically incrementing our profit, and then we can decrement our orders. And this is going to be simply width times by inventory I. Actually, yeah, I think we can just copy all of this. So copy U. So now we're going to decrement the orders because we've used this many orders up. In the case that we don't, there aren't enough orders and we have to add a partial level, we can basically get the quotient and remainder using the divmod method in Python. So we're going to say divmod and pass in orders and pass in width. And this will give us basically the whole and remainder ranges, or whole levels and remainder levels. So we're going to say, first thing we're going to do is profit. Actually, I'm just going to copy this over here. So we want to first add all of the whole levels, don't we? So we want to say inventory I minus whole plus 1. So this is going to add all of our whole levels, but we do have a remainder. Remember, we have the remainder value from the divmod function. So these are the balls that we need to add that aren't part of the full levels. So we can just say profit plus equals, and then we can add remaining. Oh, actually, is that remaining? And then, well, yeah, remainder is what it is basically. And then we can say times by. I was just looking at that. I was looking like, where have I used remainder or remaining? And then we're going to say inventory I minus 1 minus whole. Actually, no, it'll be I minus whole. So we basically want to now add the remainder levels to the remainder balls, basically to our profit. And then once we've done this, we know that we basically come to the end of our code. Basically, we don't need to go any further because we've now added our partials, which means that we've come to the end of our orders. And then the next thing we can do is simply get our profit and return the profit. But remember, there is something that we need to do. We're told over here that the value may be too large, so we want to return it mod 10 to the power of 9 plus 7. So we can just do that. Turn mod 10 to the power of 9 plus 7. So that's the code. Let's actually run the code and let's check I haven't made any mistakes. And I have made some mistakes. That should be self sum. Classic Leetcode. Okay, so, and we don't pass the test cases because it's clear. Okay, 1, 2, and 1, 4 was that expected output. Okay. So I know our arithmetic helper function is solid. We're reversing our inventory, then we're appending a sentinel. We've got our profit to 0. To I minus inventory I plus 1 is less than orders. this may be harder to debug than I thought. So inventory I minus inventory I plus 1. I'm fairly confident this sum range function call is correct. Next thing we want to do is check our order. So we want to decrement it by the number of balls. Okay, I'm confident this is correct. And we've got a whole and remainder. So okay, we are missing a plus equals operator. So we're not actually adding our remainder. That makes a lot more sense, which is why we were getting 1 and 2, but we weren't getting the last two elements in that test case. Okay, cool. So that was our only bug. Amazing. So you can see that we missed our, rookie mistake. We missed the increment operator. So yeah, not ideal, but and it took us a while to actually solve that. But I do apologize for that, and I hope the rest of the code actually makes sense. So just to go over what we were doing, because that took a slight amount of time for me to figure out. We do have a sum range helper method to return the sum of the arithmetic series, and then we are sorting the inventory from in descending order, pending a sentinel over here, just so that we have a good terminating operator, and then we are going through our inventory. If we can, we will add the entire range. Otherwise, we'll add partial ranges and then get the remainder and whole. Add all the whole levels and then add the remainder level after that. And then just return the output mod 10 to the power of 9 plus 7. So that's basically the code. And obviously, we pass all test cases for this problem. So in terms of time complexity, well, we're looking at big O of n. So we're looking at big O of n, log n, big O of n, log n for time. And space complexity is going to be auxiliary space, so it's just going to be big O of 1. So I hope this video made sense, guys. It's one of the more complicated greedy problems, and it does require a little bit of mathematical intuition, but I hope it made sense, guys, and I'll catch you in the next one.